Hello, and welcome to Acoustics Derivations. In this video, we will derive the linearized wave equation for waves in a fluid. In previous videos, we derived the continuity equation or the conservation of mass equation. We derived the conservation of momentum equation, and we derived the state equation. If you haven't seen those and you're curious where these equations came from, I would encourage you to check those videos out. Now, before we begin, I want to bring attention to this term rho B, where B is the body force. So we're going to set this term actually equal to 0 for this derivation. Because if you saw the video on the momentum equation, I said that the most common body force is gravity, and even that is not very common for most linear acoustics applications. So we will just set that term to be 0. So we want to derive the linearized, maybe I should even write that, linearized wave equation for waves in a fluid. But to do that, we need to linearize, makes sense, these equations. So to do that, we can define total pressure, P, as some static pressure, P naught, or ambient pressure, P naught, plus some perturbation pressure, lowercase p. Similarly, we can define some total density as some static density plus some perturbation density. Now, if you saw the derivation of the equation of state, then this should be very familiar to you, and I explain it in greater detail there. We can also note that particle velocity is some particle velocity u naught, some static particle velocity plus u. But it turns out that if you just think about it for a second, the static particle velocity is 0. So because there's no motion in the static medium. So we can consider particle velocity just as particle velocity. So now we're going to undergo the process of linearization. And what that means is, so we note that in these expressions here, the perturbation pressures and particle and densities, I should say, as well as particle velocity, but are really, really small. So little p, rho prime, and u are very, very small quantities. So in the process of linearization, if we ever run into 2 or more of these quantities, these perturbation quantities multiplied together, we'll set them equal to 0. Why? Well, it's an approximation, of course, but a very small number times a very small number is an extremely small number. By that logic, we can say, it's essentially 0. Let's ignore that term. So we'll begin by linearizing the continuity equation, which I will now substitute in these into the continuity equation. Okay, so, well, first, before we actually undergo the process of linearization, we need to note that the static density is independent of time, so the time derivative of the static density is 0. So from the first term, we left with d rho prime dt. Now the process of linearization comes in. So we see that there's inside this bracket here, we have a rho naught times a u and a rho prime times a u. Well, rho prime times u are 2 perturbation quantities multiplied together. And if you recall, I say that in that case, we set that equal to 0. So we're left with, and rho naught is independent of the spatial divergence. So we can move that outside and we get rho naught divergence of u. So this I will now call the linearized continuity equation. So it's the time derivative of the perturbation density plus static density times the divergence of the particle velocity is equal to 0. So we'll do the same thing with the momentum equation. Let me just write it down here, making sure to make these substitutions. Okay, so I've written down the momentum equation. Now we're going to linearize again, and we note that this term, rho prime times u, is would be nonlinear. So we have rho naught du dt, and again, the rho can come out because it's the static condition is independent of the derivative or of the time derivative, so it's independent of time. So we can obtain this. It turns out that this middle term is entirely nonlinear because we have a u times a u. So it doesn't matter if we have rho naught or rho prime, that whole term cancels. Finally, over here, the derivative of the static pressure is 0. So we're only left with gradient of pressure is equal to 0. So this we will call the linearized momentum equation. Well, it turns out that the state equation is really easy to linearize. So let me write that just right here. P is equal to rho prime C naught squared times 1 plus B over 2A rho over rho naught plus higher order terms. Well, it's really easy to linearize, and we'll call it state sub L. It's simply just the first term in this expansion. Why? Well, if you go to the next term, you have rho. Oh, sorry, this should be a rho prime. So rho prime times rho prime is a rho prime squared. That's nonlinear, so you throw it out. So let me collect all of the equations now in the linear form. So we have linear continuity is d rho prime dt plus rho naught divergence of u. We have the linearized momentum equation as rho naught du dt plus grad lowercase p is equal to 0. And we have the linearized state equation as P is equal to rho prime C naught squared. Okay, so we're not quite ready to fully derive the wave equation because we need one more step. You want to eliminate rho prime in these equations. So let's create something I'll call CL, the linearized continuity equation prime, where we now plug rho prime is equal to P over C naught squared into this P prime right there. So this is going to be 1 over C naught squared dP dt plus rho naught div u is equal to 0. So there we go. So we have this equation and this equation. Two equations, both in terms of pressure and particle velocity. So now we're ready to fully derive the wave equation. Now, the wave equation is of course presented in terms of your wave variable, which here is either pressure or particle velocity, and that's actually why we wanted to eliminate perturbation density. But here we're going to just derive the wave equation in terms of pressure. The same process will give you in terms of particle velocity, but typically we see it and use it of um, in terms of pressure. So what we're going to do is we're going to take the divergence of the linearized momentum equation, and we're going to subtract off the time derivative of the linearized state equation. Okay? So, well, let's do that. So we have that so rho naught times the divergence of the time derivative of particle velocity plus the Laplacian of pressure minus the 1 over c naught squared times the second derivative of pressure with respect to time plus rho naught times the time derivative of the divergence of u is equal to 0. Now, okay, so we're almost there. Now, if we assume that pressure and particle velocity are quote unquote well-behaved functions, in as much as they have continuous and differentiable derivatives, we note by Courant's theorem that this term and this term are equal to 0. And just as a refresher, Courant's theorem is you have some function f that is a function of x and y that you can interchange the derivatives and this at second order, and they're equal. So we are allowed to cancel those two terms, and we arrive at our linearized wave equation that the Laplacian of p is equal to 1 over c naught squared times the second derivative of pressure with respect to time. So this is our linearized wave equation in 3 dimensions. Now, it's often useful to look in 1 dimension. So if we look at 1D Cartesian, I think that's how you spell it. It is d2p dx squared is equal to 1 over c naught squared d2p dt squared, which has general solution. P is equal to f of x minus ct plus g of x plus ct, excuse me. Now, if we look at 1D spherical, of course, the Laplacian in spherical coordinates is a little bit different. So we have the second derivative of pressure with respect to the radial position r plus 2 over r times the first derivative of pressure with respect to r is equal to 1 over c naught squared d2p dt squared, which has general solution f of these should be c naughts up here, sorry. F of r minus c naught t over r plus g of r minus c naught t over r, and this is a plus r plus c naught t. Now, things get a little bit more interesting if you look at 1D cylindrical, because the wave equation in 1D for cylindrical is this. Now, this does not have a general solution like Cartesian and spherical. And I'm not going to show the math or do the math to show that, but when your radial position is much, much greater than a wavelength, you can approximate the pressure field as this. So again, this is when you're significantly far away from whatever source is generating the sound. Mathematically, we can only approximate it at that point. But again, we've derived the wave equation in 3 dimensions. And then the linearized wave equation in 3 dimensions, and then showed the Cartesian, spherical, and cylindrical cases and their general solutions if they exist, or an approximation if they don't exist. So that concludes this video. Thank you.